And in our next step, we're going to apply eigen decomposition to solving multilinear ODEs. So a multilinear ODE looks like this. So it is a linear ordinary differential equation, but y is a vector. So generally speaking, y is a vector of states, and it's coupled through the differential equation to all the other states. So if we have n states, for example, in our reactor, let's say we have concentration and temperature and pressure, for instance. So those are all states, and we are interested in the rate of change of those states with time. And each of those rates may be related to the values of the other states. And so we have a highly coupled system of equations here. And at the face of it, we don't know how to solve this because each of these involves other time functions, right? Each y here is a different time function, which we don't know at the outset. However, these are linearly related. And in fact, any system of equations locally, so near some point, we hope that we can claim that it's locally linear. But anyway, let's say for now that it is a perfectly linear system of equations. Well, we've just said, as we can see here, our A's are a matrix of constants. And so we can arrange our original system of equations into this nice compact form. And now we have our matrix A of constants. And we've just looked at the eigen decomposition. So we've said that we can create a matrix whose diagonal entries are the eigenvalues, and the V's are the eigenvectors in the column space. So these are vectors with the special property that when you multiply them by the original matrix A, you get another vector which is parallel to that original vector V. So those are the V's, and then the lambdas are the values by which you have to multiply that number to get that the new result. So anyway, that's what we discussed last time. So we have all these matrices now, and the nice part about these lambdas is that they are only non-zero on the diagonal. So in other words, you have a matrix that looks something like this. So capital lambda equals, and we can imagine here, for instance, let's just say some arbitrary constant. Then you've got zeros here. And then we have another row of such constants. Oops. We need to use a special. Let's say we have a matrix like this. Then we've got up here, we've got 2, 0, 0. So our first eigenvalue is a 2. Then let's say our next eigenvalue was a 5. And let's say the last eigenvalue was a -3, just arbitrarily choosing. Right, so that's our matrix. So it's only on the diagonal do we have non-zero values. And if we think about what that means, if you have a different system of equations where instead of this matrix A, instead of A, which has non-zeros generally everywhere, if you have this more restrained case where it's non-zero only on the diagonal, then you can see that when you multiply this out, right, for instance, you would multiply the top row 2, 0, 0 by vector Z, which is Z1, Z2, Z3, then the only term which will survive is this one. So we can write dz1 dt equals lambda1 z1. And similarly for the second one, 0, 5, 0, if you think of multiplying that with the vector z1, z2, z3, the only term that will survive on the right-hand side is 5 times z2. So dz2 dt is lambda 2 z2, and so on. So we can see that in this case, we have a nicely separated system of equations. It's not like the first system where the rate of change of y1 was related to every other variable that was possible in the system. in this case, they are all nicely separated. So if we have such a nice situation, then we can readily propose that in each case there applies a general solution. So we can see the solution here is Z1 naught e to the lambda 1 t, and here it's Z2 naught e to the lambda 2 t, and so on. So generally we can say the solution for the ith entry in our state space is Zit equals Zi naught e to the lambda it. And you can say, well, yes, that's very good, but this is isn't this just wishful thinking? And we often do that in maths, right? We have a difficult problem, then we imagine simpler versions of that and see how we can relate the two. So we've got this very nice case here. And this came from nowhere, right? We just noticed, oh, this lambda is such a nice matrix. What if we had this case instead? Well, let's see how it relates to our original case. So this lambda, we've shown through eigen decomposition, we've shown that it has this relationship to our original matrix A. So we can replace this lambda by V inverse AV. So we can rewrite this lambda Z as V inverse AV times Z, right? So we've just replaced the lambda here by this. And if we don't like this V inverse, we can multiply both sides by V. So we can write it as V times dz dt, and then left over will be AVZ. So we have that here. And then, of course, we can group these together. So V times Z is here, and you've got another V times Z here. So that's what the equation looks like now. And then let's compare that with our original function, right? So we've got V times Z here, and we've got a V times Z here. And if you compare that with our original problem, right, which just comes from this, our original problem was nothing but dy dt is ay. And if you look at this equation, you've got something, so ddt of something equals a times that same something. And so from this, we can say clearly then y equals vz. So y equals vz. And what's nice about this is we know z, we know how to solve z. We didn't know how to solve y, but we know how to solve z. And it turns out all we need to do to translate back to y is to multiply by v. And v is nothing but a matrix of constants, right? If we can find the eigenvectors of the matrix A and arrange them in the column space, then this is a known matrix of constants. So that matrix times this vector of z's. So, and these we have analytical solutions to. So it's very simple now. So in fact, all this is just repetition. So we saw this before. So we know we have those solutions, and now we just have to multiply it out like this. And so we can see here that our solution is going to be V11 e to the lambda t, right? These lambdas come from here, right? So you've got your lambda t's here, and you have to multiply by v here. And so, of course, the right-hand side is not as simple as the Z case. It's not a single term in each case, but still it's a linear combination of all these exponential terms. And these are the same exponential terms. So you've got a term here with a lambda 1t, and there's another one here with a lambda 1t. So there's a column of lambda 1t's. And so for each I, there's a column of e to the lambda t. And then we have different constants in front here. So it turns out that our solution can be obtained quite easily through this eigen decomposition. And now let's relate that to what we said earlier about the Euler's formula, right? We can see we've got these exponentials with the lambda t there. And this lambda can generally be a complex number. Right, remember when we calculate eigenvalues, if you think about that approach where you multiply diagonals and that whole procedure, and if you have to take square roots of negative numbers, then it can easily turn out that there are complex numbers among your lambdas. So that part's fine. In a way, that part doesn't worry us too much, right? This adds oscillation. So having imaginary parts means we could have some oscillations in there. But the part we're really concerned about is the benign real part. So if we have a real part here, which is positive, then that's going to show up in here, right? So if you have a real part, if A is real, and if it's positive, then we are going to have a positive number here, and it's going to be e to the positive times t. And that means that as time progresses, this term will get bigger and bigger, and our solution will explode, basically. So if there is even a single lambda value in here with a positive real part, then that term will run away to infinity. And so that's the condition of stability for us. We never ever want a positive real part in our eigenvalues, right? So that establishes the condition of stability that we'll be pursuing in the remaining lectures.